Welcome to the Python Programming Tutorial Series for Climate Mathematics Theory and Applications, Chapter 11, Python Analysis of Incomplete Data, Part 3. In this video, we will examine spatial characteristics of temperature change trends. Let's begin with Section 11.4, Spatial Characteristics of the Temperature Change Trends. First, we are going to compute the trend for each box in the 20th century. We are going to set up a variable named TIMO1, and it is going to be created from the line space between 1900 and 2000 with 1200 points in between. Temp1 will be a copy of the Temp1 we set up in section 11.3, which was in the previous video. We're just going to make a Temp1, creating that copy of that data. Next, we are going to replace the missing values with NaN in Temp1. Any value that is less than 490, we are going to input an NaN in there instead. So we're going to use a where function to do this. We're going to operate that where function on our Temp1 array with our Boolean statement being Temp1 less than, greater than, or equal to negative 490. We are inserting, which is that second parameter, a NP-NaN, which is a actual NaN value being inputted where these conditions are met. Now we're going to go ahead and set up a trend G1 variable, and it will be an array of zeros that has size 2592. Moving on, we're going to go into a for loop that grids and performs our linear regression, which fits each grid temperature over the months between January 1900 and December 1999. On a linear slope, we're going to grab those coefficients, and those coefficients are going to be saved into our trend G1 variable that is highlighted on the screen. Then we are going to use this trend G1 list, and we are going to plot it. So we're going to go ahead and set up our for loop in the following manner. For I in the range from 0 to 2592, we are going to go ahead and enter a if loop. Once we enter that for loop, we're going to set up if you are not an NP is NaN. So if this function comes back true, that is NaN function comes back true, we are negating that true statement. So it's going to be if false or if true, then we are going to enter this if loop. We are looking at column 242, which corresponds with January of 1990. And column 1441 corresponds with December of 1999. And these are going to be the temperature data for the grid point from January 1990 to December of 1991. We're going to go ahead and set up a grid temp variable, and it will be the located indices from our Temp1 array dictated by those indices we discussed earlier. We're going to filter out any month where it has an NaN value. We're going to name this IDX, and we are going to use the isInfinite function from the NumPy package on our TIMO1 variable. We are also concatenating this, sticking an ampersand in between. So if either of these come out true, then it will get saved into our IDX variable. We're going to go ahead and run that NP is finite on our grid temp as well. Next, we are going to define our IDX variable. As a result, from running our NumPy is finite function on TIMO1 and grid temp. We're going to check to see if there is at least 1 month with a non-NaN number for our linear regression. We're going to go ahead and enter another if loop using np.any, which will check for at least 1 occurrence of a non-NaN value in our IDX array. We're going to go ahead and define AB as the polynomial fit using a NumPy function, polyfit, on our time O dictated with the indices that are IDX as our X variable, and grid temp with the indices IDX as our Y variable. And we are just going to fit a first order polynomial in this case. We just want to note that AB in the 0th index has the slope coefficient saved in it. Now we're going to go ahead and fill our trend G1 by every single slope coefficient that comes out of that polyfit function that was up above the highlighted line. If we do incur a NaN value in our IDX, we're going to default to our else clause, and we are going to just simply make our trend G1 into a NP-NaN. Lastly, exiting that if-else loop, we're going to enter the last portion of our outer if loop, and this will allow us to stick in an NP-NaN into trend G1 if this original condition is not met. Once we run this, we will get an array of slope coefficients that are fit from our time O and our grid temperatures. Moving on to figure 11.11, we're going to go ahead and set up some data, make a contour map, and go ahead and plot it. We need to set up a map variable, which we are going to reshape the array that is dictated by n times 100 for n in our trend G1 array. We're going to reshape this into -1 by 72 shape, which will give us a 36 by 72 matrix out. Next, we're going to go ahead and suppress some of our numbers into the -2 to 2 range. That can be done with the highlighted function. We're going to stick a NumPy maximum around our NumPy minimum, operating both of those functions on mapmat, comma 2 within our minimum function, and then that result will have the second parameter -2 in our maximum function, and this does truly compress our numbers into the -2 to 2 range. We're going to go ahead and declare some variables in order to help set up our figure. DPI will be equal to 100. Fig is going to be our figure instance with using those DPI as our fig size. It's just going to help adjust our frame of our figure into the right type of shape for optimal plotting. We're also going to go ahead and set our axes using the add axes function in our figure instance. Moving on, we're going to create our actual base map, which will be our map of the world. We're going to call this a map, and we're going to use that base map function dictating our central longitude, latitude, and the cylindrical projection. We're going to go ahead and add coastlines, add state lines, and add country lines to our AMAP instance. And we are going to create and draw meridians and parallel grid lines using the highlighted functions on the screen. We do need to convert our latitude, longitude values to be able to plot on the XY axis that we're setting up. We're going to use that AMAP instance, and we are meshing our long1 and our lat1 variables in order to make an XY coordinate pair that has every single unique long and lat value. Python does understand this newly defined x and y as longitude and latitude values because of this AMAP function that we're wrapping around it. Go ahead and create your contour levels. We can name it clefs. And now it's time to fill our contour map. We're going to call it a CN plot, and we're going to use our base map function, which is that A map, and we are drawing a contour F map on top of it. We're going to use parameters X, Y, map, with our levels equal to C levs and our color map equal to the jet color map. We would like a color bar on this plot because we are looking at a contour plot. We just need to go ahead and use that base map function followed by the color bar function on our contour variable, where we could set the location, we could set the padding to make sure it's a little bit off of our main plot, and we could also set our ticks to whatever you desire. We're going to go ahead and add a plot title. It will be the January 1990 to December 1999 temperature trends in degrees C divided by century. Lastly, we're going to go ahead and add that X label, add a Y label, and go ahead and wrap that whole block with a PLT show. We do get this beautiful plot to pop up, which does show us our January 1900 to December 1990 temperature trends with units degrees C divided by century. Moving on, we are going to now compute trends for each box in the 20th century. Version 2, we're allowing 2/3 of our data, and that will mean that 1/3 of our data is missing. We're going to compute the trend and plot the 20CV2 trend map. All of this setup is very similar from the setup we went over up above. We have a time O variable, a temp 1 variable set up from the NP line space with our years, or grabbing that temp 1 data from our temp matrix that was created in the previous video. We're going to replace our missing values with NANs just like we did above, using those highlighted lines. This time we are going to name our zeros count of not missing, and this is going to be a zeros array that has size 2592. We do want to count the number of missing data points, and we can do so by running this highlighted for loop. We're going to let the count of not missing at each index be equal to the temp TF with location I with all columns. We're taking these values that are found in this indice and we are converting them to a list and then counting which ones have a false or no value input. Next, defining a trend 20C empty array. It's going to have zeros in it, and it is going to have the length of 2592. This for loop that is highlighted on the screen is very similar to the for loop that we were counting the missing data in the previous blocks. We're just going to go into the for loop, into the if loop, and then if this condition is met, then we enter this for loop, which we are setting up our grid temp, which will be our Y values in our polynomial fit. We are also setting up that IDX, which will tell us the index of where we actually have numbers rather than NaN values. And then we are setting up an AB variable, which will be the linear regression slope coefficient. And then finally, sticking that linear regression slope coefficient into our trend 20C on the ith index. If we did not satisfy this condition that is highlighted, we're going to default to the else condition, and that is where we're setting that value of trend 20C equal to the NPNAN. We could go ahead and verify our shape of temp 1, and we truly do get a shape of 2,592 by 1,200. Moving on to figure 11.12, we're going to go ahead and set up our map, set up our figure, and go ahead and draw a contour F of our linear regression coefficients. We're going to reshape the trend 20C array into a 36 by 72 matrix. Then we are going to take all of those values in this newly set up matrix and divide by 10. Next, we're going to compress all the numbers into the negative 0.2 to 0.2 range by the highlighted line. Setting up our figure, setting that DPI equal to 100, setting up our fig instance by that PLT figure function with a specified fig size, and also adding our axes in the highlighted text. Next, we're going to go into the creation of our base map, which we are going to be using the projection cylindrical and also the central point dictated by the rest of those parameters. We're going to draw our coastlines and country lines. We are also going to add some meridians and parallels onto our map. Next, we need to convert that latitude and longitude values into our XY variables using that base map instance on our mesh grid function that will create every unique pair between long 1 and lat 1 and also convert them into a latitude longitude coordinate pair, which will now be named X and Y. Next, setting up our contour levels and getting to our contour plot. We're going to name our contour plot CN plot when we are using that base map instance F map and drawing the contour F function on the XY coordinate with map mat overlaid on it using the levels dictated by C levs and the color map dictated by the jet color map. We do need to add a color bar, which it's very similar addition as we did in the plot above. Lastly, adding some labels, we need to add our title, our X label, and our Y label. And wrapping that whole thing with a PLT show, we do get January 1900 through December 1990 temperature trends with units degrees C divided by decade. Moving on, we are now going to do a very, very similar plotting mechanism between the years 1976 and 2016. We're going to grab that data from the temp array, which is dictated by the highlighted indices. We could go ahead and find where we have NAN values and go ahead and save the Boolean assignment of where those NAN values occur. We're going to go ahead and go into the count of not missing. Just like we did above, you could go ahead and just follow that for loop that we created above. This highlighted block will save all of the linear regression slope coefficients between 1976 and 2016 that are dictated by the linear regression fit with time 01 and our grid temp variable. We could go ahead and check the shape of that. We do get a 2,592 by 492 matrix to pop up. Moving on to figure 11.13, This setup is very similar to the setup we had before, setting up that map variable into a 36 by 72 array, using that array that popped out of that for loop up above that was named trend 20C. We're suppressing our values into the -4 to 4 range this time, setting our DPI, setting up our figure instance, adding those axes, using a cylindrical projection for our map creation, adding coastlines, state lines, and country lines, also adding parallels and meridians. Then we can go ahead and convert our latitude longitude into that XY coordinate pair using the fmap on our mesh grid function, setting our contour levels and drawing our filled contours using that contour f function on parameters xy by my map. Then we could go ahead and add our color bar using the color bar function, add a title to our plot, and also label our X and Y axes appropriately. Lastly, wrapping that whole thing with a PLT show, we do get a January 1976 to December 2016 temperature trends, degree C divided by decade plot to show. This concludes Chapter 11, Python Analysis of Incomplete Data, which is the final chapter of Climate Mathematics, Theory, and Applications. Thank you for listening.